Hey guys, before this video starts, thank you. Just for being here, for watching, for caring. If you want to do more, Patreon link is in the description.
There is something particular about the weight of a hand pressed flat against a table. Not the table itself or the grain of it, the temperature, whether it is oak or something cheaper, but the resistance, the way the surface pushes back, the way your hand knows, without being told, that there is a boundary here, that space ends at this point and something else begins. It is one of the oldest sensations available to a body, and it is, in a way, the first measurement any of us ever took of the universe. Here, not here, the geometry of existing in a place. You've been doing this your entire life, measuring, not with instruments, with the length of a reach, the arc of a step, the distance from one wall to another in a room you've walked through 10,000 times. 3 numbers. That is what it takes to locate anything. How far left or right? How far forward or back? How far up or down? 3 directions, 3 degrees of freedom, and somewhere early, very early, probably before language, this became the shape of the world, not a theory, a fact, not something you were taught, something the body just accepted. This is the agreement, and most of us never question it. There is something I want to mention before we begin. This channel is kept alive by the people who choose to support it. No outside funding, no sponsorships. We are approaching 200 members on Patreon, and that is the number where this project moves from fragile to stable. For those who support, I build things alongside these episodes. Comparison PDFs on things like black holes and neutron stars. Audio biographies of scientists whose names history almost erased. Research notes from every video on this channel, and extended audio pieces for subjects too expansive for a single episode. If you want to help get us that number, the link is in the description. Tonight, on The Sleepy Physicist, we are going to follow that agreement to its edge, and then a little past it. The room you are in right now has 3 dimensions. You know this the way you know your own name. Not because you have checked recently, but because nothing has ever suggested otherwise. The ceiling is above you. The walls are at a distance. The floor holds you in a direction called down. These are not observations. They are the background. The thing everything else is placed against. But here is the part that starts to feel strange if you sit with it long enough. We did not discover that space has 3 dimensions. We assumed it. The assumption came first. The mathematics came later, much later. And it did something odd. It did not confirm the assumption so much as inherit it. Euclid described 3-dimensional geometry in the 3rd century BCE, not because he had measured the dimensions of space and found exactly 3. He described it because 3 was the number of directions his body understood. And for a very long time, for almost all of human history, that was sufficient evidence. It is the sort of thing that feels obvious until you notice it. And then it feels, maybe, slightly less obvious. The physicist Hermann von Helmholtz spent a significant amount of the 1860s and the 1870s thinking about what a being confined to a 2-dimensional surface would experience. He imagined creatures living on the surface of a sphere, able to move forward, backward, left, right, but with no access to the dimension perpendicular to their surface, not blind to it exactly, constitutionally unable to point in that direction, unable to form the concept of that direction. The 3rd dimension would not be invisible to them. It would be, in some strict sense, unthinkable. Helmholtz was not making a point about spherical creatures. He was making a point about us. What if our 3-dimensional intuition is exactly as complete as a flat creature's 2-dimensional intuition? What if the directions we can point in are the directions our nervous systems evolved to navigate, and nothing more? This is not a philosophical question dressed up as physics. It is a physics question dressed up as something that sounds too strange to take seriously at first. But it has been taken seriously. For over a century now, it has been taken very seriously indeed. The world feels 3-dimensional. The world has always felt 3-dimensional. And feelings, as it turns out, are not measurements. Here is what a dimension actually is when you strip away the intuition. A dimension is a direction in which something can move, a degree of freedom, a way of varying position without varying any other coordinate. 1 dimension means you can move along a line. 2 means you can move across a surface. 3 means you can move through a volume. But the mathematics that describes dimensions does not care about the number 3. There is nothing in the equations that makes 3 special. You can write consistent self-contained geometry for 4 dimensions, 5, 10, 26. The shapes are harder to picture. In fact, at a certain point they become impossible to picture, but they are not harder to describe. The mathematics runs cleanly at any number. This is the thing that took a long time to absorb, historically speaking. Our senses report 3 dimensions. The mathematics is comfortable at any number. And so the question that turns out to have been sitting there all along, is this. Are we experiencing the full geometry of space, or are we experiencing the fragment of it that our bodies are built to detect? That question sounds abstract. It isn't. Or it wasn't, once physicists started following it seriously in the 20th century. Once they followed it seriously, it stopped being a curiosity and started being a structural problem. The kind of problem you cannot unknow. Press your hand flat against the nearest surface. Whatever is closest, or a mattress, a wall, a blanket pulled across your knees. Notice the resistance, the pressure, the way the surface reports its own existence through your palm. This is the sensation that built the 3-dimensional model of the world. This is the data. This stubborn, physical pushback against a hand. And for most of human history it was enough. More than enough. It was everything. But the universe turns out to be less interested in what our palms can feel than in what the equations require, and the equations, as we're going to spend a great deal of time discovering, require something stranger than a table's surface can communicate. They require a space with more directions in it than your hand can press against. They require dimensions that are present at the surface of every object woven into every point of space, and yet somehow unreachable by any nervous system that evolved to find food and avoid falling. The stage, as it turns out, has a great deal more backstage than the stage suggests, and the backstage has a shape, a very specific, very strange, very mathematically precise shape. But that comes later. For now, just notice the weight of your hand, the particular resistance of a surface that knows where it is, and let the thought that this might not be the whole story settle somewhere quiet without rushing to resolve it. It will not be resolved tonight, but it will, slowly, become clearer. Theodore Kaluza was not, by most accounts, the most prominent physicist of his era. He was not attached to the great centres of theoretical physics in the way that made careers move quickly in the early 20th century. He worked in Königsberg, which is now Kaliningrad, a Russian exclave on the Baltic coast, though in 1921 it was still Prussian, still cold in the particular way that coastal cities in winter are cold, still the kind of place where a mathematician could sit with an idea for a very long time without being disturbed by anyone who might tell him it was too strange to pursue. He was a private Dozent, which is a German academic rank that means something like present at the university, permitted to teach, not yet secure enough to be considered permanent. It is a rank that involves a particular kind of patience, and Kaluza, it seems, had that patience in abundance. What he also had in 1919 was a thought. The thought was this: Einstein's general relativity, published in full in 1915, described gravity as the curvature of 4-dimensional space-time, 3 spatial dimensions and 1 of time, bending in response to mass and energy. It was a stunning piece of work, strange, geometrically demanding and correct in ways that kept being confirmed. But it described only gravity, electromagnetism, the force governing light, electricity, magnetism, sat alongside it in a separate framework, described by Maxwell's equations, well understood and stubbornly unconnected to Einstein's geometry. 2 forces, 2 separate mathematical descriptions, no bridge between them. Kaluza's thought and it is a sideways kind of thought, the sort that arrives not from pushing hard in an obvious direction, but from noticing something peripheral, was this. What if there is a fifth dimension? Not a time dimension, a spatial one, a fifth direction in which nothing we can detect actually moves, but which exists in the mathematics of the universe nonetheless. And what if, when you write Einstein's gravitational equations in 5 dimensions instead of 4, and then ask what the equations look like when projected back down to 4 dimensions, what if the projection produces, automatically, without any additional assumptions, Maxwell's equations for electromagnetism, which is exactly what he found? Or, and this is the part that takes a moment to absorb, he found that the mathematics allowed it, that the structure was there, that gravity and electromagnetism, when viewed from a 5th dimension, were not 2 separate forces at all. They were 2 different faces of a single geometric object. In April of 1919, Kaluza wrote a letter to Einstein. Not a paper, a letter. He had worked out the mathematics carefully enough to believe the result was real, but cautiously enough to want to test it against someone whose judgment he trusted before committing it to formal publication. The letter described the 5-dimensional framework, the projection, the appearance of Maxwell's equations from what should have been purely gravitational geometry, and then Kaluza sent it, and waited. Einstein did not respond for 2 years. 2 years. It is hard to know exactly what that silence felt like from Königsberg. Einstein was not ignoring the letter, see. He later said he had found the idea striking enough to think about at length, which, given what Einstein was thinking about at length in that period, is not a small thing. But from Kaluza's end, there was just the waiting, the working, the continuing to sit with an idea that had not yet been confirmed or rejected by anyone else in the world, because no one else in the world had seen it. There is something about that image, the letter in transit or read or sitting on a desk somewhere in Berlin or wherever Einstein happened to be, that resists easy description. A thought that had taken years to form, written out carefully on paper, sealed, sent, and then nothing. Just the continuing rotation of the planet and the continuing weight of not knowing. In 1921, Einstein wrote back. He told Kaluza the idea was worth publishing. Kaluza's paper, Zum Unitätsproblem der Physik, which translates roughly as On the Unity Problem of Physics, appeared that year in the Proceedings of the Prussian Academy of Sciences. What Kaluza had done was something that physics had not, at that point, quite done before. He had added a dimension to reality not because he had observed it, not because any experiment had suggested it was there, but because the mathematics became more unified when it was included, and he trusted that unification as a signal worth following. This is a particular kind of intellectual move. It is not, strictly speaking, empirical. It is closer to aesthetic, in the sense that it privileges elegance and coherence as guides toward truth, which sounds like the sort of thing that should make a careful scientist nervous. And maybe it should. I am not entirely sure it doesn't, even now. But the history of physics in the 20th century suggests that this kind of move has been, despite everything, quietly productive. The extra dimension was not, in Kaluza's original paper, given a size or a physical explanation. It was just there, in the equations, carrying the electromagnetic force the way a coat pocket carries something you put in it without thinking. Present, doing a job, not yet asked how it had come to be so small that no one had ever detected it. That question would come next, but it would come from someone else, a few years later, in a different city, with a different set of tools. For now, the thing to sit with is the letter itself, the act of writing down something you cannot yet prove in a way anyone else will immediately accept, and sending it to the one person whose opinion you most want, and waiting 2 years for a reply. And continuing to work during those 2 years. And the reply, when it came, being, yes, this is worth pursuing. That is not a story about genius exactly. It is more a story about a particular kind of stubbornness, the unhurried, non-dramatic kind that keeps returning to a problem not because it is certain of the answer, but because the question will not quite go away. The 5th dimension was proposed in a letter, accepted 2 years later, published quietly, and then, for a moment, left sitting there, like an idea that had arrived slightly ahead of its context, waiting for the rest of the framework to catch up. Kaluza's fifth dimension had a problem, not a mathematical problem. The mathematics was clean. The problem was physical, and it was the kind of problem that makes an idea go from interesting to unacceptable very quickly if no one addresses it. If there is a fifth spatial dimension, why has no one ever moved in it? Why does no experiment, no observation, no falling object or orbiting planet show any trace of a direction that should by all geometric reasoning be available? Kaluza had not really answered this. He had imposed something called the cylinder condition, a requirement that nothing in the physics should depend on position along the fifth dimension, which made the equations work, but which was more of a constraint bolted onto the theory than an explanation arising from it. It was, if you wanted to be critical about it, the mathematical equivalent of saying, assume the problem away and look how clean the result is. Oscar Klein did not assume it away. In 1926 he asked why. Klein was a Swedish physicist, working in the quantum mechanical tradition that was, in 1926, actively dismantling classical intuitions about how small things behave. Quantum mechanics had just finished one of its most productive years, Heisenberg's matrix mechanics in 1925, Schrödinger's wave equation in 1926, the probabilistic architecture of the subatomic world taking shape in real time. Klein had been sitting inside that framework, and when he turned to Kaluza's fifth dimension, he brought quantum reasoning with him. Here is what he noticed. In quantum mechanics, a particle confined to move in a closed loop, a circle, cannot take any energy it likes. Its momentum is quantized. It can only have values that fit an integer number of wavelengths around the loop. This is a hard constraint. The smaller the loop, the larger the energy gap between allowed states. Wind the loop down small enough and the energy required to excite even the first quantum state above the ground state becomes enormous, far beyond what any physical process at ordinary temperatures or energies could supply. Klein applied this to Kaluza's fifth dimension. Suppose the fifth dimension is not extended, not infinite, not even large. Suppose it is closed. Suppose it loops back on itself, like a circle attached to every point in ordinary four-dimensional space-time, but wound so close that its circumference is comparable to the Planck length, roughly 10 to the power of minus 33 centimeters, a number so narrow it barely qualifies as a number in any sense a body can hold. At that scale, the quantum energy required to detect the fifth dimension, to send anything around it, to excite any motion in that direction, is so far beyond any energy available to any experiment that has ever been, or is likely ever to be conducted, that the dimension becomes, for all practical purposes, inaccessible. Not invisible exactly. Inaccessible. There is a difference, though it is a difference that may not matter. Wind a thread around a cylinder tightly enough and it disappears, not because it isn't there, because the resolution of your eye cannot separate the windings. Klein's argument was structurally similar, except the cylinder is the dimension itself, and the eye is every instrument humanity has ever built or could build within any foreseeable energy range. The cylinder condition that Kaluza had bolted on as an assumption now had a physical grounding. If the fifth dimension is compactified and wound into a circle small enough, then nothing we can probe will ever feel it vary, not because the variation is forbidden, but because reaching it requires energy we do not have. The condition emerges, it is not assumed. It falls out of the geometry and the quantum mechanics together. This is the mechanism. Small enough, and a dimension hides itself. There is something slightly uncomfortable about this, and it is worth naming even briefly. A hidden dimension that is hidden by being too small to ever detect is, at least in principle, indistinguishable from a hidden dimension that does not exist. Klein's argument explains why we would not see it. It does not on its own prove that it is there. The compactification is a consistent picture, it is self-contained. But consistency is not the same as confirmation. Klein seems to have understood this, or something like it. The theory was compelling and the mechanism was elegant, maybe too elegant, the kind of cleanness that occasionally means you have built something airtight rather than something open to the world. But the mathematics ran, the quantum argument held, and the idea that a spatial dimension could be present at every point in space, while remaining permanently, structurally beyond reach, that idea was now, for the first time, a serious physical proposal rather than a speculation. What Kaluza had proposed, Klein had explained, not proven, explained. The fifth dimension, if it existed, was folded, wound close against itself at each point in space, present everywhere, accessible nowhere. And this arrangement, Klein showed, was not arbitrary. It was what quantum mechanics would predict for a dimension of that scale. 6 extra dimensions would come later. The reasons for 6 rather than 1 would take another 60 years to fully emerge. But the logic Klein established, that a dimension can be compactified, that compactification has a quantum mechanical justification, that smallness is a form of concealment rather than absence, that logic would carry forward into everything that followed. The mechanism was in place. What remained was to find out what the hidden space was actually shaped like. There is a version of physics where particles are points, infinitely small, dimensionless, located at a precise coordinate in space, with no internal structure whatsoever. This is the version that worked for most of the 20th century. It is the version encoded in the Standard Model, that extraordinarily precise, slightly ungainly framework that describes 3 of the 4 fundamental forces and all the matter we have ever directly detected. Point particles, no size, no extension, just a location, a set of quantum numbers, and a set of interactions. The problem with point particles is not that they are wrong exactly. It is that they carry inside certain calculations a particular kind of mathematical injury. When you try to calculate the energy of 2-point particles interacting at very short distances approaching 0, the result does not converge. It grows without limit. The mathematics breaks down at the point of closest approach, producing infinities that have to be managed by a procedure called renormalization, which works, and which many physicists find slightly uncomfortable, and which the physicist Richard Feynman once described with a phrase that was not complimentary. String theory's opening move is to replace the point with an extended object, a string, one-dimensional with a length tiny but non-zero. And this replacement, this seemingly small geometric adjustment, turns out to change the character of the calculations in ways that run much deeper than the original motivation suggested. A string can vibrate. A point cannot. This is the thing. When a string vibrates, it vibrates in modes, different patterns of oscillation, each with a different energy, each corresponding, in the theory, to a different particle. The electron, the photon, the graviton, not separate fundamental objects, but different harmonics of the same underlying structure. This is the central claim, and it is strange enough to require sitting with rather than moving past quickly. But here is where the dimension question enters. Because when you write down the mathematics governing how a relativistic string propagates through space-time, how it moves, how it vibrates, how its quantum states are counted, the equations have what are called conformal symmetries. Symmetries that describe how the string's internal description of itself relates to the external description of its motion through space. And these symmetries produce, in the quantum mechanical treatment of the string, certain terms, correction terms, anomaly terms, numbers that arise from the quantization procedure, and that, if they are non-zero, indicate that the theory is internally inconsistent, that it contradicts itself at a mathematical level deep enough that no physical interpretation can rescue it. The condition for consistency, for these anomaly terms to vanish, fixes the number of dimensions, not suggests, not prefers, fixes. In bosonic string theory, the earliest and simplest version, the anomaly cancels in 26 space-time dimensions, not 25, not 27, 26. The calculation is exact. In superstring theory, the version that incorporates supersymmetry and is capable of describing fermions, the matter particle, the number is 10, 9 spatial dimensions and 1 of time. The anomaly cancels there and only there, and the theory is consistent there and only there. Think of it this way. And I'm reaching for something approximate here, not a precise analogy. Think of a bridge cable under tension. There is one specific tension at which the cable holds the load it is designed for, carries the frequency of vibration it is engineered to carry, and remains stable under the forces applied to it. Too loose and it sags incorrectly, and the harmonics are wrong. Too tight and it fails at the anchor points. The correct tension is not a preference, it is the only tension at which the structure works. The number of dimensions in string theory is like that. 10 is not chosen. 10 is the tension at which the string equations hold. This requires sitting with, because it inverts the ordinary relationship between a physical theory and the world it describes. Normally, we observe the world, extract its properties, and build a theory to match. We notice that space appears three-dimensional, and we write three-dimensional equations. The number of dimensions is an input, something we put into the theory based on observation. But string theory does not work this way. The number of dimensions is an output. The internal consistency of the mathematics, the requirement that theory not contradict itself, produces a specific number, and that number is 10. The world must have 10 space-time dimensions for string theory to be a coherent framework. Not because we chose 10, but because the equations refuse to close at any other count. Which means that if string theory is correct, and this is a substantial if, one that the field has been negotiating with for decades, then 6 spatial dimensions exist that we have not observed. Not might exist. Do exist. The theory does not make them optional. They are part of the structure. Required by the same logic that requires the graviton to appear in the spectrum of string vibrations, the same logic that makes the anomaly terms vanish when the count is right. 6 extra spatial dimensions, somewhere. The question that follows immediately, and it followed immediately for the physicists working through this in the 1970s and 1980s, is why we don't see them. Why does space feel three-dimensional, if it is in fact 9-dimensional? And here the logic that Klein established 50 years earlier becomes newly relevant. The dimensions are there, but they are compactified. Wound into shapes so narrow that no probe at any energy we can generate has yet resolved them. The Kaluza-Klein mechanism, developed for a single extra dimension in 1926, now had to accommodate 6 at once. 6 dimensions, wound close, present at every point in space, at this point in the room, inside the air between you and the ceiling, in the structure of every atom in your body, but wound into a geometry so particular, so narrow, that the entire history of experimental physics has passed through them by us without noticing. That is, I am not sure what word fits to there. Strange seems too small, but it is accurate. It is the word that is actually correct. The 6 dimensions are not added to make the theory more interesting. They are not a theoretical flourish or a speculative extension. They fall out of the arithmetic the way a remainder falls out of a division. The theory is consistent in 10 dimensions. We observe 4. The remaining 6 are somewhere in the geometry. What geometry exactly, that is the question. And it turns out to be a question that mathematics had already been working on in a completely different context for 30 years before anyone thought to connect the two. That connection, when it came from an unexpected direction, as connections in physics often do. The obvious move, once you accept that 6 spatial dimensions need to be compactified, is to reach for the simplest shapes available. A sphere, a torus, a cylinder. The geometric objects that are, in some sense, the first ones a mathematician reaches for when asked to describe a compact space. Closed, smooth, well understood, carrying no surprises in their structure. These are the shapes that have been studied for centuries. Their properties were catalogued, their symmetries were known, and in the early years of string theory compactification, physicists tried them, not carelessly. Carefully, with the full apparatus of the theory applied to each candidate, checking what the resulting 4-dimensional physics looked like when 6 dimensions were wound into each shape. The results came back wrong. not approximately wrong, not wrong in ways that might be adjusted with a small correction or a parameter choice, wrong in a specific structural way that pointed directly at something the universe insists upon and simple compact shapes cannot provide. The problem is handedness. Your left hand and your right hand are geometrically related. One is the mirror image of the other, but they are not interchangeable. You cannot rotate a left hand in three-dimensional space until it becomes a right hand. The transformation that connects them requires a reflection, a flip through a mirror plane, and that operation is not a rotation. This distinction between something and its mirror image is called chirality. And the weak nuclear force, one of the four fundamental forces, is chiral. It does not treat left-handed and right-handed particles the same way. The W boson, which mediates the weak force, interacts only with left-handed particles, not with right-handed ones, never with right-handed ones. This is not a small asymmetry that gets corrected at higher energies or in more precise experiments. It is a structural feature of how the weak force works, confirmed in experiment after experiment since the 1950s, when Chien-Shiung Wu demonstrated parity violation in cobalt-60 decay, and the physics community had to absorb the fact that nature has a preference, a stubbornly, specifically left-handed preference at the level of the weak force. The universe is not symmetric under reflection. It knows the difference between left and right. Simple compact shapes do not know this difference. When you compactify the 6 extra dimensions on a sphere, or a torus, or most of the other geometrically natural candidates, the resulting four-dimensional theory preserves a symmetry between left-handed and right-handed particles. The shapes are too symmetric. They are, and this is the word that kept appearing in the technical discussions of the time, not as a metaphor but as a precise mathematical descriptor, non-chiral. They produce a four-dimensional physics in which every particle comes paired with its mirror image partner, in which the weak force has no preference, in which parity is conserved. Our universe does not look like that. Our universe is chiral. The weak force is chiral. The 3 generations of quarks and leptons are chiral. Whatever shape the 6 extra dimensions are wound into, it cannot be a shape that preserves the symmetry between left and right, because the physics it produces must break that symmetry, must produce a world in which the W boson only notices left-handed particles, must reproduce the specific fussy-handedness that experiment has confirmed at every energy we can reach. A sphere cannot do this. A torus cannot do this. Flat compact spaces cannot do this. The simplest shapes are the wrong kind of right. They work in many respects. They produce compact spaces that satisfy several of the requirements, and then they fail at this one thing, which turns out to be the thing that cannot be negotiated. There is a particular texture to this kind of failure, not the clean failure of something that is simply incorrect from the start. That is almost easier, because it points clearly away. This is the failure of something that is mostly correct. The shape is compact, it has the right number of dimensions. The mathematics of the compactification runs without contradiction. And then you extract the particle content of the resulting four-dimensional theory and find it wearing the wrong-handedness, like a glove that fits every finger except it is for the wrong hand. You cannot fix it by adjusting the size of the shape. You cannot fix it by choosing a slightly different version of the same geometry. The problem is not in the parameters. It is in the topology, the fundamental shape of the space itself. This is what made it a real problem rather than a technical inconvenience. The sphere was tried. It failed. The torus was tried, actually several variants of the torus, flat compact spaces with different identifications, different ways of stitching the edges together. They failed. Orbifolds, which are spaces constructed by taking a simpler shape and imposing a discrete symmetry on it, producing something like a sphere with corners. These were tried. Some of them got closer. Some produced theories that were almost chiral, that had the handedness almost right, that preserved supersymmetry in almost the right way. Almost. That word kept appearing. That was the texture of the period. The shape needed to be compact. It needed to satisfy the equations of string theory. It needed to preserve enough supersymmetry that the resulting four-dimensional theory was tractable, not fully supersymmetric, which would make it too symmetric to match reality, but partially supersymmetric, with supersymmetry broken in a controlled way. And it needed to be chiral. It needed to be a shape that knew the difference between left and right, that produced a four-dimensional particle spectrum with handedness, that could in principle give rise to the specific asymmetric structure of the weak force. No simple shape satisfied all of these simultaneously. What was needed was a shape that was, in some geometric sense, inherently twisted. Not twisted in the casual sense, in a precise mathematical sense, a shape with a topological structure that breaks mirror symmetry at the level of the space itself, that cannot be reflected into a copy of itself by any continuous transformation. A shape that is, at its core, one-handed. Such shapes existed in mathematics. They had been studied, in a completely different context, for reasons that had nothing to do with physics. They had names and properties and a small community of mathematicians who found them worth understanding. Nobody had yet thought to apply them to the 6 missing dimensions of string theory. That was about to change. But first, someone had to believe the shapes could exist at all, which, for a time, was not obvious. Princeton, in the early 1950s, had a particular atmosphere that is difficult to reconstruct accurately, and probably too easy to romanticize. The Institute for Advanced Study sat at a slight remove from the university campus, deliberately, by design, to give its members the kind of distance from ordinary academic obligation that pure thought was supposed to require. The building was quiet in the way that buildings are quiet when the people inside them are working on things they cannot yet explain to anyone else. Chalk dust, long stances in seminar rooms, the specific hush of mathematics being done at a level where even colleagues in adjacent fields had only a partial view of what was happening. Eugenio Calabi arrived in this environment carrying a question. He was not in 1953 a young unknown. He had trained carefully, worked seriously, published work on differential geometry that the community recognized as careful and technically accomplished. He was not operating from the margins, but the question he had arrived at, the conjecture he was beginning to articulate, was the kind of question that put him in a strange position, because the answer he suspected was true was also the answer that most of his colleagues, when they heard it, suspected was false. The question concerned curvature, specifically a type of curvature called Ricci curvature. In general relativity, Ricci curvature is the mathematical object that describes how space-time bends in the presence of mass and energy. Einstein's equations relate it directly to the distribution of matter. Where there is matter, Ricci curvature is non-zero, space bends, and gravity results. In empty space with no matter present, the equations permit Ricci curvature to be zero. This is the vacuum case, Latin the Ricci sense, which does not mean flat in the ordinary visual sense. A space can be Ricci flat and still have a complicated, twisted, folded geometry. Ricci flatness is a specific technical condition about one particular measure of curvature, not about overall shape. Calabi was working with complex manifolds, geometric spaces that are built not from real coordinates but from complex ones, spaces where each point is located using numbers that have both real and imaginary components. These spaces have a richer structure than ordinary Riemannian manifolds, partly because of this complexity, and partly because of an additional structure called a Kähler metric, a way of measuring distances and angles that is compatible with the complex structure in a very precise sense, that respects the complex geometry at every point. What Calabi conjectured in 1953 was this: that on a compact Kähler manifold satisfying a certain topological condition, specifically that a particular class associated with the manifold's curvature is trivial, there exists a unique Kähler metric whose Ricci curvature is identically zero, not approximately zero, not zero in some average sense, zero everywhere at every point simultaneously, Ricci flat, throughout, on a space that is compact, closed, finite in extent, with no boundary. The reaction broadly was skepticism, not hostile skepticism, not dismissal, The mathematical community in the 1950s was not in the habit of rudeness about careful conjectures from established colleagues. But the conjecture was saying that something existed which seemed on the face of it unlikely. A compact space with no curvature in the Ricci sense is a strange object. Intuitively, an intuition in mathematics is unreliable but persistent. A compact space that folds back on itself, that has no boundary, that is closed, seems like it ought to curve, seems like the closing and the folding would produce curvature. The expectation from differential geometry's accumulated instincts was that this kind of flatness in a closed space would be very hard to achieve. Calabi was asserting that it was not only achievable but guaranteed for any manifold meeting the topological condition. Not just one example, an entire class. And he was asserting it without, as yet, a proof. The conjecture sat there, unproven, neither confirmed nor refuted, waiting. What made it stranger was that Calabi seemed, by most accounts, quietly certain. Not certain in a way that produced impatience or defensiveness when challenged. Certain in the way that some mathematicians carry a belief that has arrived through a kind of geometric intuition deeper than the formal proof. A sense that the structure of the space permits the conclusion that the topology and the complex geometry are arranged in a way that makes Ricci flatness not just possible but necessary, for reasons that a proof would eventually make explicit. He had worked through enough of the structure to believe the result was there. He could not yet show it to anyone's full satisfaction, but he did not stop believing it. This is a particular position in mathematics. Not comfortable, exactly, but not unbearable either. The conjecture existed. It was precise. It was either true or false. Time would eventually produce someone who could determine which. The Hodge theory that Calabi's conjecture drew on, the framework developed by W.V.D. Hodge in the 1930s connecting the topology of complex manifolds to the analysis of differential forms, had established a set of techniques for understanding how certain structures on manifolds relate to their global topology. Calabi had grown up mathematically inside this tradition, had attended seminars where these tools were being actively refined, and his conjecture can be read as a natural question arising from that framework. Given everything Hodge theory tells us about compact complex manifolds, what can we say about the metrics they can carry? What is the most geometrically disciplined metric such a space can support? Ricci flatness was the answer he arrived at. Not smoothed over or approximately flat. Exactly, provably, everywhere flat in the Ricci sense. The conjecture waited, through the mid-1950s, through the 1960s, into the 1970s. 20 years of mathematical work around it and adjacent to it. But the central claim that these Ricci flat calorimetrics exist on compact complex manifolds with the right topological class remained unproven. The shapes Calabi had proposed existed only as a conjecture, beautiful in the way that precise mathematical claims are beautiful, but not visually, not emotionally, but structurally. The way a locked room is beautiful if you believe the right key exists. Someone would have to find the key, and the person who eventually found it had, for a time, believed it didn't exist at all. In 1973, Xing-Tung Yau stood at a geometry conference and announced that Calabi's conjecture was false. He had not proven it was false. He had found what he believed to be the shape of a counterexample, a mathematical argument suggesting that the kind of Ricci flat calorimetric Calabi had conjectured could not exist on the class of manifolds Calabi had proposed. The argument was incomplete, as arguments presented at conferences often are, but Yau was confident enough in its direction to say so publicly. Calabi was in the room. He did not object. And for a moment it seemed like one of those episodes in mathematics where a conjecture simply turns out to be wrong. Interesting to have considered, but ultimately pointing nowhere. Yau went home and kept working. What happened over the next few months is the part that is harder to describe without making it sound more dramatic than it actually felt from inside, which was probably just the slow grinding texture of mathematical work, checking, rechecking, following the consequences of the argument to see what else it implied. What it implied, as Yau followed it, was increasingly strange. The supposed counterexample kept producing results that didn't fit. Not wrong in an obvious way, but wrong in the way a measurement is wrong when it is just slightly off from what the instrument should read. Wrong in a way that accumulates as you push further into the calculation. The argument against Calabi's conjecture was not holding up under sustained examination. Not because Yau had made a careless error at the conference, because the structure of the mathematics, examined more carefully, was pointing in the opposite direction from the one he had announced. He had been wrong, publicly wrong, at a conference where Calabi had been present. There is a particular kind of intellectual honesty that this situation requires, and it is not the dramatic kind that gets described in terms of courage or nobility. It is quieter and more uncomfortable than that. It is the kind that requires sitting with the fact of the error long enough to understand it fully, rather than finding a way to reframe or minimize it. Yau had announced a disproof of Calabi's conjecture. The disproof was wrong, and the implication, the one that the mathematics kept insisting on the more he looked, was that Calabi's conjecture might actually be true, that the shapes Calabi had proposed might actually exist, that the result he had tried to refute was pointing stubbornly toward existence rather than impossibility. He reversed course, not quietly, not without acknowledgement. In later accounts, he was direct about what had happened at the conference and what the subsequent work had shown. But the reversal was not a public event. It was a private reorientation, followed by 3 years of sustained technical effort aimed no longer at disproving the conjecture, but at constructing the proof of it. 3 years, that is a long time to work on one problem. The technical difficulty of what Yau was attempting was concentrated in a particular type of partial differential equation, the complex Monge-Ampère equation, which governs the relationship between a Kähler metric and its Ricci curvature. Proving Calabi's conjecture required showing that this equation, on any compact Kähler manifold with the right topological class, has a smooth solution. Not approximately, exactly. A solution that exists, is unique, and is as geometrically well behaved as the conjecture required. No one had ever solved an equation of this specific type in this specific setting before. The tools needed to do it had to be, in some cases, developed as part of the proof itself, which is the sort of thing that is easy to say and very slow to do. The work involved gradient estimates, pseudo estimates, a careful analysis of how solutions behave at the limits of the relevant function spaces. It was dense. It was technical in a way that most people working in adjacent areas of mathematics could follow only in sections, and it went on for 3 years. This is what sustained mathematical effort looks like from the outside. Not elegant, not swift. A long, close, mostly invisible engagement with a problem that does not offer encouragement and does not signal its own resolution until suddenly, in a way that is almost never as clean as it sounds afterward, something closes. On Christmas Day 1976, Yau met with Calabi and another mathematician to go through the proof. It was Christmas Day. Presumably the institutional buildings were quiet in the way they are quiet on public holidays, the particular silence of corridors that are usually populated and aren't, the odd flatness of spaces designed for activity when no activity is happening. I almost didn't mention the date. It seems like the kind of detail that gets used to make a story feel significant. But it is the actual date, and there is something in it, not symbolic, just factual. That the confirmation of a 23-year-old conjecture happened in that specific quietness, with no ceremony, among 3 people going through mathematics together. Calabi confirmed the validity of the proof. The conjecture was true. The Ricci flat Kähler metrics existed, not just one, but an entire class of them, on every compact Kähler manifold satisfying the topological condition Calabi had specified. The shapes were real, not physically real, not yet, that would come later, but mathematically real, proven to exist, no longer merely conjectured. Yau published the full proof in 1978. The Fields Medal followed in 1982. Awarded in part for the Calabi conjecture proof, the mathematics' highest recognition given to mathematicians under 40 for work of exceptional significance. The citation noted the proof alongside Yau's work on the positive energy theorem in general relativity and several other contributions. It was a broad acknowledgement of a body of work. But the Calabi conjecture proof was, among these contributions, the one that would eventually reach furthest. The shapes that Calabi had proposed and Yau had proven, compact, Kähler, Ricci flat, were thereafter called Calabi-Yau manifolds. Not because anyone chose the name formally, but because it is the name the mathematical community converged on naturally, in the way communities name things that belong to two people equally. And for a few years, they remained purely mathematical objects, interesting to geometers, studied for their own properties, not yet connected to the 6 missing dimensions of string theory, not yet understood as candidates for the shape of hidden space. That connection had not yet been made. The proof was complete in 1976. The connection would come 9 years later in a paper by 4 physicists who had been working on a different problem entirely and found, somewhat to their own surprise, that the shapes they needed had already been proven to exist. The mathematics had arrived before the physics knew it was needed, which is not, in the history of these two fields, as unusual as it sounds. But it is still, each time it happens, a slightly strange thing to notice. By 1984, theoretical physics had developed a specific kind of restlessness. The Standard Model was complete, more or less. The Higgs boson was still undetected, but theoretically in place. The gauge structure of the 3 forces was understood. The particle content was catalogued. It was a framework of extraordinary precision and a certain aesthetic ungainliness, a collection of pieces that worked together, without anyone having a deep explanation for why those particular pieces, why those particular force strengths, why 3 generations of quarks and leptons rather than 2 or 4. It described the world accurately and explained it only partially. And gravity sat outside it entirely, described by general relativity, incompatible at the quantum level, connected to the rest of physics by observation and disconnected from it by mathematics. String theory in 1984 was not yet the dominant theoretical framework it would briefly become. It had been developed through the 1970s by a relatively small community, and it had a reputation, and not entirely unfair, for mathematical elaborateness in excess of physical prediction. But in 1984 something shifted. Michael Green and John Schwartz published a paper showing that a specific version of superstring theory, the one with gauge group SO32, was free of the quantum anomalies that had made string theories seem potentially inconsistent. The anomaly cancellation worked. The theory was consistent, and another version, with gauge group E8 times E8, turned out to be anomaly-free as well. This is what gets called the first superstring revolution, which is a dramatic name for what was, from the inside, probably more like the sudden acceleration of work that happens when a field senses that the path it has been on is not blocked. Philip Candelas was at the University of Texas at Austin. Gary Horowitz and Andrew Strominger were at the University of California, Santa Barbara. Edward Witten was at Princeton. They were not, as far as the available accounts suggest, a preformed collaboration that had been working toward this specific result. They were 4 physicists who were, each in their own way, thinking about the implications of the 1984 anomaly cancellation results, specifically about what the heterotic string theory with gauge group E8 times E8 required as a background spacetime. The theory demanded 10 dimensions, 4 were observed, 6 needed to be compactified, and the compactification space needed to satisfy a set of conditions that fell out of the requirement that the resulting 4-dimensional theory preserve something called n equals 1 supersymmetry, not full supersymmetry, which would produce a theory too symmetric to match the observed particle spectrum, but a specific partial amount that would keep the theory tractable while allowing the symmetry breaking necessary for realistic physics. The condition for n equals 1 supersymmetry in 4 dimensions, derived from the string theory equations, required the compactification manifold to have SU3 holonomy, which is and here is the moment that must have had a particular quality to it. the moment of recognition, exactly the condition that Yau had proven 9 years earlier characterizes Calabi-Yau manifolds. The key had been cut before the lock was built, and in 1984 and into 1985 these 4 physicists found the lock. The paper appeared in 1985. Vacuum Configurations for Superstrings, Nuclear Physics B, volume 258, pages 46 through 74. The title is technical and dry in the way that physics paper titles often are. It does not announce itself, does not signal what it contains beyond the immediate technical description. The paper itself is dense, careful, and in its implications the first of its kind. What the paper showed, working through the mathematics of heterotic string theory, compactified on a Calabi-Yau manifold, was this. The resulting 4-dimensional theory has gauge group E6, with matter in the 27-dimensional representation of that group. And the thing the paper kept returning to in different ways, was that the structure was compatible. Compatible with having the right number of generations of particles, compatible with preserving the right amount of supersymmetry, compatible with producing a 4-dimensional physics that bore, at least in outline, a structural resemblance to the Standard Model. Not identical to the Standard Model, not a derivation of it in any complete sense. But the first time in the history of physics that a fundamental theory, a theory proposed not to describe the Standard Model, but for independent mathematical reasons, had produced, from its own internal logic, a 4-dimensional structure that looked like it was in the neighbourhood of what actually exists. I want to be careful here, because the temptation is to describe this as more complete than it was. The 1985 paper was not a derivation of the Standard Model. It was a demonstration that deriving something like the Standard Model from string theory was not, in principle, impossible, that the framework was capable of producing 4-dimensional physics with the right rough features. The distance between capable of producing and actually producing turned out to be very large, larger in some ways than the optimism of 1985 quite anticipated. But even with that caveat in place, something had happened that had not happened before. The 6 missing dimensions of string theory had been given a shape, not a unique shape. Calabi-Yau manifolds were already known to be numerous, and the 1985 paper did not select one over others, but a class of shapes, a mathematically precise class of compact 6-dimensional spaces that satisfied the requirements of the theory, that were consistent with the observations, that produced 4-dimensional physics carrying at least the structural echo of the world we inhabit. This is still, 4 decades later, the most promising contact point between string theory and the observable universe. Other approaches have been developed, other compactification schemes explored, other geometric backgrounds studied. But the Calabi-Yau compactification of the heterotic string, the thing the 4 physicists paper established, remains the prototypical case. The one that is studied first, returned to most often, used as the benchmark against which other proposals are measured. In the years immediately following 1985, the field accelerated. Hundreds of Calabi-Yau manifolds were catalogued. The question of which one described our universe, if any did, became suddenly intensely active. Seminars that had been modestly attended filled. The community of people working on string compactification grew quickly, with the specific urgency that attaches to a field that believes it may be near something. That urgency would, over time, encounter the specific difficulties that come with any framework of this ambition. The landscape problem would emerge. The question of testability would sharpen. The distance between the theory and the experiment would prove, in many respects, greater than the optimism of 1985 had suggested. But in 1985, in the specific moment of the paper, there was something else. There was the recognition, quiet in the way that significant things sometimes are, not announced but present, that a mathematical object proven to exist 9 years earlier, in a completely different context, had turned out to be exactly the object that a physical theory needed. that the geometry Calabi had conjectured and Yau had proven was the geometry that the universe, if string theory was right, was actually using. That is the thing the paper established. Not a complete theory, not a final answer, but a connection, exact, mathematical, and pointing somewhere that physics had not been able to point before. Before anything else, a small admission. Six-dimensional geometric intuition is not something a human nervous system possesses. We navigate three spatial dimensions with our bodies, build models of four-dimensional space-time with effort and abstraction, and beyond that, the honest answer is that we are working with mathematics that describe something we cannot picture in the way we picture a room or a mountain or the surface of a sphere. The geometry of Calabi-Yau manifolds lives in 6 real dimensions. What follows is the best available approach to it, which involves analogy, consequence, and a willingness to hold concepts that do not fully resolve into images. With that said, let us start with flatness, because flatness is where the confusion begins. When physicists say that a Calabi-Yau manifold is Ricci flat, they do not mean flat in the way a table is flat, or a calm lake is flat, or the way a sheet of paper is flat before you fold it. Those are ordinary flatnesses, a surface with no curvature at all, extending uniformly in its plane, going nowhere interesting. Ricci flatness is a different, more specific, more technical condition. And understanding what it actually means requires separating two things that are easy to confuse: local curvature and global shape. Imagine running your hand along a curved surface in the dark. You cannot see the shape, but you can feel it. The pressure in your palm changes as the surface rises or falls, the way your fingers have to adjust an angle to stay in contact with something that is not planar. That pressure information, integrated across a small region of the surface, is what curvature means locally. It is the way space bends at a point, measured precisely enough to distinguish between different types of bending. Ricci curvature is one particular way of measuring this local bending. A mathematical object that, in general relativity, captures how volumes of space are distorted by the presence of matter or energy. In empty space in a vacuum, Einstein's equations require the Ricci curvature to be 0. The space can still have shape, it can still be curved in other ways. But the specific distortion that Ricci curvature measures, the volume distortion, the way nearby paths diverge or converge, that must be absent. A Calabi-Yau manifold satisfies this condition everywhere, at every point simultaneously. Not because it is a vacuum in any physical sense, but because its geometry is arranged in a way that satisfies the vacuum equations by construction. It is a compact space, closed, finite, without boundary, that is nevertheless Ricci flat throughout, which is, when you stop to consider it, a strange achievement. The closing of the space, the way it folds back on itself, should produce curvature. Intuitively, it seems like it ought to. That it does not, that the geometry can be arranged to fold and close without producing Ricci curvature anywhere, is the content of what Yau proved, and it remains, even understood mathematically, slightly surprising. The second property is the Kähler structure, and this one requires introducing a different kind of geometry. Ordinary Riemannian geometry describes spaces using real numbers, coordinates that measure position along each dimension, distances computed from a metric that assigns a length to each small step through the space. Complex geometry adds a layer to this by building the space from complex coordinates instead of real ones. Coordinates that carry both a real and an imaginary component, doubling the structure available at each point. A Kähler manifold is a complex manifold with a metric, a way of measuring distances, that is compatible with the complex structure in a very particular sense. The compatibility condition is demanding. It requires that the complex structure and the metric be threaded together so precisely that neither distorts the other as you move through the space. The complex rotation at each point, the operation of multiplying coordinates by the imaginary unit, must be preserved by the metric, must look the same from every point, must not twist or skew as you move from place to place. This compatibility is what gives scalar manifolds their distinctive character. It is what makes them, among complex manifolds, the ones with the most controlled geometry. And it is what makes them suitable for the kind of precise, constrained compactification that string theory requires. The Kähler structure keeps the 6 dimensions orderly, in a way that allows the 4-dimensional physics to be extracted without the geometry introducing its own uncontrolled distortions. Calabi-Yau manifolds are Kähler manifolds. The Kähler structure is not added to them. It is part of what they are. And combined with Ricci flatness, it produces a space with a very specific geometric character. Compact, complex, internally consistent, curved in some ways but not in the Ricci way, structured in a manner that is both highly constrained and this is the part that takes time to absorb but enormously varied. The third property is holonomy, and this is where the geometry becomes briefly vertiginous. Holonomy describes what happens to a geometric object, to a vector, a direction, when you carry it around a closed loop in a space and bring it back to where it started. In flat, ordinary space, this is uninteresting. You pick up a vector, carry it around a loop, return to the start, and the vector points in exactly the same direction it pointed when you left. Nothing has happened. The space has no curvature to rotate the vector as it travels. In a curved space, something different occurs. Carry the vector around a loop, and when you return, it is rotated. The amount of rotation depends on the curvature enclosed by the loop, how much the space bends inside the path you traced. The set of all possible rotations you can generate this way, across all possible loops in the space, forms a mathematical group called the holonomy group. It is, in a precise sense, a fingerprint of how the space curves. For Calabi-Yau manifolds, the holonomy group is SU3, a specific named mathematical group that describes a particular kind of rotation in 6-dimensional complex space. SU3 holonomy is a very restrictive condition. Most 6-dimensional spaces have larger holonomy groups, more general rotation sets. SU3 sits inside the larger possible group, a special subgroup, with more symmetry, more constraint. What SU of 3 holonomy produces, physically, is the preservation of exactly one covariantly constant spinor, one geometric object that does not change as you carry it around any loop in the space. And this, translated into the language of string theory, is what preserves n equals 1 supersymmetry in the resulting 4-dimensional theory. The holonomy group of the compactification manifold controls how much supersymmetry survives the compactification. SU3 gives you just enough. One preserved spinor, one surviving supersymmetry, a 4-dimensional theory that is constrained enough to be tractable and unsymmetric enough to resemble reality. It is a very specific condition to satisfy, and Calabi-Yau manifolds satisfy it. That is part of what they are. Put these 3 properties together, and what you have is this: a compact 6-dimensional space built from complex coordinates with a Kähler metric compatible with the complex structure, satisfying Einstein's vacuum equations at every point with holonomy group exactly SU3. A space that is closed without being flat in the ordinary sense, that is curved in some ways and not in others, that carries a very particular geometric symmetry at every point, and that can, in principle, take an enormous variety of specific shapes while satisfying all of these conditions simultaneously. That last point is worth pausing at. The conditions are extremely restrictive. Ricci flat Kähler manifolds with SU3 holonomy. The intersection of these requirements is small, relative to all possible 6-dimensional spaces, and yet within that intersection there are thousands of distinct topological types, possibly tens of thousands, each with its own specific shape, its own Hodge numbers, its own Euler characteristic, its own particular arrangement of topological features. The same set of constraints that makes Calabi-Yau manifolds geometrically distinctive also permits, within those constraints, an extraordinary diversity of forms, which is either reassuring or troubling, depending on what you wanted the theory to say. If you hoped that the constraints would select a unique shape, the one shape that describes our universe, the diversity is a problem. If you suspected that the richness of the observed world might require a rich geometric source, the diversity is at least not surprising. What is not in question is the geometry itself. The shapes are real, in the mathematical sense. They satisfy precise conditions. They carry specific properties. And they are, given what string theory requires of a compactification space, exactly the objects the theory needs, not by coincidence, not by selection, but because the conditions that define them are the conditions the physics imposes. The shapes exist. They are constrained. They are varied. And at every point in space, if the theory is right, one of them is present, folded into 6 dimensions, too narrow to resolve, carrying in its topology the structure of the physical laws we observe. There is a way of looking at the world that most people never quite arrive at, not because it is hidden or difficult to access, but because nothing in ordinary life makes it necessary to so. It is the view from topology, from the branch of mathematics concerned not with the specific measurements of a shape, not with its size or its angles or the precise curvature of its surface, but with the features that survive every possible continuous deformation. The features that are present in a shape regardless of how you stretch it or bend it or compress it, as long as you do not tear it or puncture it or glue parts of it together that were not connected before. A sphere and a cube are topologically identical. You can deform one into the other continuously, and every topological feature is preserved across the deformation. A torus, the surface of a donut, is topologically distinct from both. It has a hole, not a hole in the material sense, not an absence of stuff, but a hole in the topological sense, a closed loop that cannot be continuously contracted to a point. You can run a finger around the inside of a torus, around the hole, not along the surface, and the loop you trace is a topological feature of the space. It is there in the shape, present in the geometry, and no amount of bending or stretching will remove it without tearing. This is what topology measures, not the shape exactly, the structure beneath the shape, the features that persist when everything that can change does change. Calabi-Yau manifolds are topologically complex in the precise sense of that word. They carry topological features that are counted by objects called Hodge numbers, a pair of integers, written H11 and H21, that measure specific aspects of the manifold's internal structure. Hodge numbers count roughly the number of independent ways the manifold can be deformed, the number of geometrically distinct parameters that describe its shape. H11 counts the ways the Kähler structure can vary, the degrees of freedom in the size and shape of the two-dimensional topological features embedded in the manifold. H21 counts something similar for the complex structure, the ways the three-dimensional topological features can vary. These numbers are topological invariants. They do not change when you stretch or bend the manifold. They are fixed by the topology, by the global structure of the space, the arrangement of its holes and handles and the relationships between them, and they are, in string theory compactification, directly connected to the physics that emerges in 4 dimensions. The number of certain types of particles in the resulting 4-dimensional theory, certain matter fields, certain moduli, certain scalar degrees of freedom, is determined directly by the Hodge numbers. Different Calabi-Yau manifolds with different Hodge numbers produce different particle contents. The topology of the hidden dimensions is not background information. It is the source of the particle spectrum. But the deepest connection, the one that is, in some sense, the claim of this chapter, runs through a different topological invariant, the Euler number. The Euler number, or Euler characteristic, is a single integer that encodes something about the overall topological structure of a space, a combination of Hodge numbers, constructed in a way that captures a global feature of the manifold's topology. For a Calabi-Yau threefold, the Euler number is calculated from the Hodge numbers as twice the difference between H21 and H11. Its value can be positive, negative, or 0, and it varies across different Calabi-Yau manifolds. In the simplest models of heterotic string compactification, the class of models descending from the 1985 Candelas-Horowitz-Strominger-Witten paper, the number of generations of matter particles in the four-dimensional theory is equal to half the absolute value of the Euler number, not approximately, not in some limit. Exactly. The count of matter generations is a topological quantity. Our universe has 3 generations of quarks and leptons, 3, the electron and its heavier copies, the muon and the tau, the up quark and its heavier copies, 3 complete sets of matter particles, each set a structural repetition of the last at higher mass. The reason the periodic table has the structure it has, the reason chemistry exists in the particular form it takes. 3. This is not a number that particle physics on its own explains. The standard model accommodates 3 generations, does not derive them. It does not explain why 3 rather than 2 or 5 or 1. In string theory compactified on a Calabi-Yau manifold with Euler number plus or minus 6, the number of generations is 3. The absolute value of the Euler number divided by 2 gives the generation count. A manifold with Euler number 6 produces 3 generations of matter, automatically. From the topology, let that sit for a moment without rushing to resolve it. The number of times matter repeats itself in our universe, the reason there is a muon as well as an electron, a charm quark as well as an up quark, may be a consequence of a topological integer, a feature of the shape of 6 hidden dimensions that no experiment has directly detected. The count of 3 is written into the geometry, if this framework is correct, the way the number of holes in a torus is written into its topology. It is there in the shape, not adjustable, not a parameter that was chosen, fixed by the global structure of the compactification manifold. This is the claim. It is stated plainly because it does not need elaboration to be strange. The periodic table of elements, the structure of chemistry, the reason you are made of the specific matter you're made of, these trace back through layers of physical law to the 3 generations of quarks and leptons, and the 3 generations may trace back to a topological integer in a 6-dimensional shape too small to resolve at any energy available to current or foreseeable experiment. I want to be precise about what this claim is and what it is not. The geometry is consistent with 3 generations. A Calabi-Yau manifold with the right Euler number produces a 4-dimensional theory with the right generation count. This is not the same as saying the geometry uniquely demands 3 generations. There are other Calabi-Yau manifolds with Euler numbers of plus or minus 4, plus or minus 8, plus or minus 10 producing different generation counts. The framework permits 3. It does not alone select 3 over the others. That distinction matters. The connection is real and specific. It is not in its current form a derivation. Beyond the generation count, the Hodge numbers determine more. The number of scalar fields in the low-energy theory, the moduli, the fields that describe the size and shape of the Calabi-Yau itself, is set by H11 plus H21. The number of certain vector multiplets, fields carrying force information, is connected to H11. The full particle content of the 4-dimensional theory, matter fields, force carriers, scalar degrees of freedom, is encoded in the topological data of the manifold. Different manifolds, different spectra. This means that the forces of nature, not just their existence but their structure, the specific gauge groups they form, the representations in which matter appears, are, in string theory, consequences of geometry. The strong force, the weak force, electromagnetism, their presence in the 4-dimensional theory depends on the topology of the compactification and the way the gauge bundle, a mathematical object defined on the Calabi-Yau, is structured. The Euler number is a stubborn little integer, fixed and immovable once the topology is chosen, and it carries in its value a count of the matter generations that is not adjustable without changing the manifold entirely. What the chapter has been building toward, without quite naming it until now, is this. The laws of physics may not be fundamental in the sense of being irreducible givens. They may be geometric consequences, the 4-dimensional shadow of a 6-dimensional topology that we cannot observe directly. The specific form of the standard model, the specific count of matter generations, the specific structure of the forces. These may be readable in principle from the Hodge numbers and Euler characteristic of the manifold that is folded into every point of space. This is either the deepest insight in the history of physics or a very elaborate consistency, and distinguishing between those two possibilities is, as yet, not something the theory alone can do. The geometry writes the laws. Whether it is the geometry of our universe that does so, that is the question that remains and has not yet been answered. The word mirror, in ordinary use, implies a reflection that is recognizably related to the original. You look into a mirror and you see something that has your face, your posture, the arrangement of your features, reversed left to right, but unmistakably derived from you. The relationship is visible. The connection is immediate. Mirror symmetry in the context of Calabi-Yau manifolds is not quite like that. The two manifolds in a mirror pair do not look like reflections of each other in any visual sense. They do not share an obvious structural resemblance. They are, by the ordinary measures of geometry, their Hodge numbers, their topological features, the arrangement of their holes and handles, different objects. In some cases, substantially different. A manifold with Hodge numbers, 1, 101, is paired with a manifold with Hodge numbers 101, 1. The first has one parameter describing its scalar structure and 101 describing its complex structure. The second has these reversed. They are not similar shapes. They are shapes in which a specific numerical relationship has been exchanged. And yet, in string theory, compactifying on one of these manifolds produces exactly the same four-dimensional physics as compactifying on its mirror. Not approximately the same, not the same in some limit or at some energy scale. The same. The particle content, the force structure, the interactions, the symmetries, every physical observable that can be extracted from the string theory is identical whether you use the manifold or its mirror. Two geometrically different objects. One physical theory. This is the kind of equivalent that takes time to accept, not because it is difficult to state, but because the implications keep expanding the longer you sit with them. Think of two musical instruments that look entirely unlike each other. Different materials, different shapes, different sizes, built on different principles, and yet when played produce not just similar sounds but physically identical acoustic outputs, indistinguishable by any measurement. Your ear, a spectrometer, any device you choose, all report the same sound. The instruments are different. The music is not. What does that tell you about the relationship between instrument and music? What does it tell you about which description is fundamental? The same question arises here, and it does not have an easy answer. The discovery arrived in stages. By the late 1980s, physicists working on string compactification had accumulated enough examples of Calabi-Yau manifolds to notice patterns in the data. Specifically, that many manifolds seemed to appear in pairs where the Hodge numbers were exchanged. H11 of one equaled H21 of the other, and vice versa. The distribution of all known Calabi-Yau manifolds, plotted by their Hodge numbers, showed a symmetry about the diagonal that was too consistent to be coincidental. In 1990, Brian Greene and Ronan Plesser published the paper that gave this phenomenon its name and its first rigorous construction. Duality in Calabi-Yau moduli space, Nuclear Physics B338. The paper showed explicitly how to construct mirror pairs, how to take a given Calabi-Yau manifold and produce its mirror, the specific geometric transformation that exchanges the two types of Hodge numbers while preserving the string physics. The term mirror symmetry entered the literature here, coined not for the visual resemblance but for the structural exchange, the way the two manifolds reflect a specific mathematical relationship rather than a geometric image. What Greene and Plesser established was the existence of mirror pairs and a method for finding them. What came next was something neither they nor anyone else had quite anticipated. In 1991, Philip Candylus, Xenia de la Ossa, Paul Greene and Linda Parks used mirror symmetry to make a prediction, a mathematical prediction, in a domain that had nothing obviously to do with string physics, the counting of rational curves on the quintic Calabi-Yau threefold. Rational curves are specific geometric objects embedded in a Calabi-Yau manifold, roughly the simplest possible curves the manifold can contain, characterized by their degree. Counting how many rational curves of each degree a given manifold contains is a classical problem in algebraic geometry, one that mathematicians had been working on for decades. For the quintic, a particular Calabi-Yau manifold defined by a degree 5 polynomial equation in four-dimensional complex projective space, the counts for low degrees were known but painfully difficult to compute. The number of degree 1 rational curves on the quintic was known to be 2,875, the number of degree 2 curves 609,250. The degree 3 count had not been established. Candelas and collaborators approached this through mirror symmetry. On the mirror of the quintic, the calculation that corresponded to counting rational curves was a different calculation entirely, a calculation involving period integrals, which are integrals of holomorphic forms over the manifold's cycles, and which were, on the mirror side, tractable in a way the direct counting was not. Using the mirror manifold, they computed not just the degree 3 count, but a formula that generated the counts for all degrees simultaneously. The degree 3 number they extracted was 317,206,375. Mathematicians working independently through conventional algebraic geometry methods initially disagreed. A group at Berkeley produced a different number for the degree 3 count. For a brief period, the physics prediction and the mathematical calculation sat in contradiction. Then the mathematical calculation was found to contain an error. When it was corrected, the answer was 317,206,375, exactly the number the mirror symmetry calculation had produced. This is the moment worth pausing at, not because the number itself is significant, but because of what it demonstrated. A technique derived from string physics, from the requirement that compactifying on a manifold and its mirror produces identical theories, had solved a pure mathematics problem that mathematics on its own had failed to solve. The physics had arrived at the answer first. The geometry of a hidden extra dimension, approached through its mirror, had unlocked a calculation about curve counting that had been open for years. If you're finding this video worthwhile, consider supporting the Sleepy Physicist on Patreon. The link is in the description. The implication that settled slowly afterward was this. If two geometrically different manifolds produce identical physics, then physics cannot on its own tell you which manifold the universe is actually using. The string theory living on the quintic and the string theory living on its mirror are the same theory. They are not two descriptions of two different physical situations, they are two descriptions of one physical situation, expressed in different geometric languages. Which geometry is real? Both. Neither. The question, and this is the part that the field has not fully resolved, may not be well posed. If the observable physics is identical, then asking which geometry the universe prefers may be like asking which coordinate system the universe prefers. Coordinates are descriptions, not facts. Geometries in the context of mirror symmetry may be the same. The universe may not distinguish between the two, not because it is indifferent, but because, from the perspective of physics, there may be nothing to distinguish. The two manifolds are not two answers to the same question. They are one answer, expressed twice. That is strange. Quietly, persistently strange. The kind of strange that does not resolve into comfort the longer you examine it, but which becomes, over time, a different kind of familiar. The familiar of a fact you have accepted without fully understanding. What the mirror world tells us in the end is that the relationship between geometry and physics is less straightforward than it seemed in 1985. The physics does not determine the geometry. The geometry underdetermines the physics in one direction and overdetermines it in another. And somewhere in that asymmetry, a question sits that the theory has not yet answered. The hope in 1985 was for uniqueness. Not stated as a hope exactly, not written into the papers or announced at the conferences as a desire, rather than an expectation. But it was there in the texture of the work, in the implicit assumption that carried the field forward. That string theory, if it was the correct framework for quantum gravity and everything else, would eventually select a single vacuum, a single configuration of the extra dimensions, a single compactification manifold, a single set of physical laws. One answer. The mathematics would close around it. The theory would point finally to the one universe it described, which would turn out to be ours. This is what a final theory was supposed to do. Not just be consistent with the observed world, but demand it. Not just permit the electron's mass and the strength of the strong force, but derive them from first principles as the unique output of the framework. The hope was that asking, why does the universe have these laws, would eventually have the answer, because it could not have had any others. The landscape is what happened instead. To understand what the landscape is, you need to hold two things simultaneously. The first is the diversity of Calabi-Yau manifolds, the tens of thousands of topologically distinct compactification spaces, each producing different four-dimensional physics, different particle spectra, different force structures. This diversity alone was already a complication, but it was a manageable complication in principle. If the theory eventually selected one manifold over the others, if some dynamical mechanism, some physical principle, picked out a unique vacuum, then the diversity of the manifold space would be a backdrop, not a problem. The second thing is flux. Inside a Calabi-Yau manifold, threaded through its topological holes, its cycles, the higher dimensional analogues of the loops you can draw on a torus, there can exist quantized fluxes, fields in the string theory sense that thread through the topology the way a magnetic field threads through a loop of wire. These fluxes are quantized, they take integer values, not continuous ones. Each topological cycle in the manifold can carry a flux of 0 or 1 or 2 or 3, up to some maximum value set by the theory's consistency. A typical Calabi-Yau threefold has on the order of several hundred independent cycles. Each cycle can carry a flux taking roughly 10 possible values. The number of distinct flux configurations is therefore, and here is where the calculation becomes a felt thing rather than just a number, 10 raised to the power of several hundred, which is in rough terms 10 to the 500th power. Written as numeral with the digit 1 followed by 500 zeros, 10 to the power of 500. The number of atoms in the observable universe is approximately 10 to the power of 80. The landscape contains 100 million distinct vacuum configurations. These two numbers are not different in the way that large numbers are usually different from each other. The landscape is not a few orders of magnitude larger than the atomic count of the universe. It is larger by a factor of 10 to the power of 420, a number so far beyond ordinary scale that the comparison almost loses meaning. The atomic count of the universe against the landscape is not even a rounding error. It is nothing. Each of these 10 to the power of 500 vacua corresponds to a different compactification, a different choice of manifold, a different flux configuration threading through its cycles. Each produces a different set of physical laws, different particle masses, different force strengths, different cosmological constant, different everything. The vacuum selection problem is this. String theory, as currently understood, provides no mechanism to select one of these vacua over the others, no dynamical principle, no energetic preference, no mathematical condition that picks out our specific configuration from the 10 to the power of 500 alternatives. The landscape is not a space of possibilities from which the theory chooses. It is a space of possibilities in which the theory is, as yet, silent about which one is realized. This is a particular kind of problem, not the kind where the theory is wrong, the landscape configurations are all internally consistent, all genuine solutions to the string equations. Not the kind where more work will straightforwardly resolve it. The vacuum selection problem has been known in something like its current form since the early 2000s, and the field has not converged on a solution. It is the kind of problem that changes what you thought the theory was. The hope was for a theory that derived our laws. The landscape offers a theory that permits our laws among 10 to the power of 500 others and says nothing so far about why ours specifically. There are two broad responses to this situation, and both are held by serious physicists, and they point in genuinely different directions. The first response is that the landscape represents a failure of predictivity that should be taken seriously as a problem with the theory. A framework that is consistent with 10 to the power of 500 different universes is, in a precise sense, not making predictions about this one. It can accommodate any observation, because with enough vacua, some vacuum will produce any physical law you care to write down. Accommodation is not prediction. A theory that fits everything explains nothing. And the landscape, on this view, is a symptom of a framework that has become too flexible to be falsifiable. The second response is that the landscape is not a failure but a discovery. If 10 to the power of 500 vacua exist, and if cosmological dynamics, specifically the process of eternal inflation, in which different regions of an eternally inflating universe nucleate into different vacuum states, allows all of them to be realized in different domains, then the landscape is not a problem to be solved. It is a physical fact about the structure of reality. The multiverse in this view is not a speculation. It is what the theory predicts. And the question of why our universe has these laws has the same structure as the question of why we live on this planet rather than another, an anthropic selection from a large but finite set of possibilities. The anthropic argument produces its own discomfort. It explains our laws by noting that we are here to observe them, which is true, but which feels, to many physicists, like the abandonment of explanation rather than its completion. If any universe consistent with observers will be observed by those observers, then the question why these laws is answered by because you could not be asking the question in any other. Which is logically correct and scientifically. It is hard to know what to do with it honestly. Leonard Susskind, who has been among the most vocal proponents of taking the landscape seriously as a physical proposal, has described the resistance to the landscape as a form of nostalgia, a preference for the universe to be smaller and more comprehensible than it might actually be. This framing has not satisfied the critics, who respond that science requires falsifiability, and a theory whose predictions are distributed across 10 to the power of 500 unobservable vacua is not, in any practical sense, falsifiable. Both positions are held with genuine conviction. Neither has been refuted. The landscape has been a feature of the string theory discussion for over 2 decades now, and it has not resolved into consensus. It has simply remained, a large, inescapable feature of the theoretical terrain, the kind of problem that does not go away because it cannot be wished away. The mathematics that produces it is solid. The physical implications are disputed. The philosophical consequences are still being worked out. What the landscape did, whatever else it did, was end the hope of uniqueness in its original form. The dream of a theory that would derive our specific laws from first principles, that would close around a single vacuum the way a proof closes around a single conclusion, that dream did not survive contact with the flux landscape. Something more complicated replaced it. More honest, perhaps. Certainly less comfortable. The question of why the universe has these laws, and not others, remains. It has not been answered by the landscape. It has been reframed. The landscape does not answer the question. It changes its shape, and sitting with a question whose shape has changed, without a new answer to fill the space, is where the field has been for some time now. Where it goes from here is genuinely unknown, not as a rhetorical gesture toward mystery, actually unknown. The landscape is real, the vacuum selection problem is real, and the resolution, if there is one, has not yet arrived. When the 6 dimensions compactify, when they fold into the Calabi-Yau geometry at every point in space, they do not simply disappear from the physics. They leave residue. This is not a metaphor. It is a structural feature of what compactification means. When a higher dimensional theory is reduced to 4 dimensions by Curling the extra dimensions into a compact space, the geometry of that compact space encodes information about its own shape. The size of the manifold, the volumes of the various cycles threading through its topology, the complex structure parameters that describe how the space is bent, all of these become, in the four-dimensional effective theory, dynamical quantities. Fields. Scalar fields, with no spin, distributed through the four-dimensional space-time, each one encoding a specific geometric degree of freedom of the hidden six-dimensional space. These are the moduli fields. The word moduli comes from the mathematical term for the parameters that describe the shape of a geometric object. The moduli space of a Calabi-Yau manifold is the space of all its possible shapes, the collection of all distinct geometries satisfying the Calabi-Yau conditions. Each point in moduli space corresponds to a specific manifold with specific Hodge numbers, specific cycle volumes, a specific complex structure. And each of these parameters, when the theory is reduced to 4 dimensions, becomes a field. A scalar degree of freedom propagating through ordinary space-time, potentially observable, potentially cosmologically significant. A typical Calabi-Yau compactification produces dozens of moduli fields, sometimes hundreds depending on the Hodge numbers of the manifold. They are at the perturbative level, before quantum corrections and flux effects are included, massless. They have no potential energy. They can take any value without the theory preferring one over another. This masslessness is protected by a symmetry, a remnant of the higher dimensional gauge symmetry that governed the original 10-dimensional theory, expressed in 4 dimensions as a shift symmetry that prevents the moduli from acquiring mass through ordinary perturbative corrections. Massless scalar fields propagating through the universe are a cosmological problem, not a small problem, a large one, with a name, the cosmological moduli problem. Here is why. In the early universe, during and after inflation, the moduli fields are generically displaced from the values they will eventually settle into. The values corresponding to the minimum of their eventual potential, once flux effects and non-perturbative corrections are included, and the moduli are stabilized. A displaced scalar field oscillates. It rolls toward its minimum and overshoots, rolls back, overshoots again, oscillating like a weight on a spring while the universe expands around it. These oscillations carry energy. The field behaves in this regime like a pressureless fluid, its energy density diluting with the expansion of the universe at the same rate as matter. If the moduli fields are massive enough, if the moduli stabilization mechanism gives them sufficient mass, they eventually decay. They couple to other fields through gravitational strength interactions, which means the coupling is weak, which means the decay is slow, which means they decay late, very late. The decay products inject entropy into the universe at a time, after Big Bang nucleosynthesis potentially, when the ratios of light elements have already been set. Injecting entropy at that point disrupts those ratios in ways that are inconsistent with observation. Or if the moduli decay before nucleosynthesis, the lightest supersymmetric particles produced in the decay can be overproduced, yielding a dark matter density far in excess of what we observe. The cosmological moduli problem is, in its bluntest form, this. The moduli fields that emerge naturally from Calabi-Yau compactification tend to produce cosmological consequences in the early universe that conflict with observation unless the moduli masses and decay channels are arranged with some care. It is a real constraint on string compactification, not a theoretical nicety. The geometry of the hidden dimensions has to be compatible not just with the particle physics we observe today, but with the cosmological history that produced that particle physics. Now the axionic partners. Each moduli field, each real scalar encoding a geometric degree of freedom of the Calabi-Yau, comes accompanied by an axionic partner. This arises from the structure of the 10-dimensional theory. The higher dimensional fields that reduce to moduli in 4 dimensions are generically complex. The real part encodes the geometric parameter, a cycle volume, a metric coefficient. The imaginary part is an action, a scalar field with a shift symmetry, protected from acquiring mass by that symmetry, able to acquire a small mass only through non-perturbative effects that break the symmetry at an exponentially suppressed level. Axions are dark matter candidates, not because they were invented for that purpose. The axiom was originally proposed by Roberto Peccei and Helen Quinn in 1977 to solve the strong SUPI problem, the question of why the strong nuclear force does not violate the symmetry between matter and antimatter the way the weak force does. The Peccei-Quinn axion became a dark matter candidate somewhat incidentally when it was realized that axions produced in the early universe would be cold, non-relativistic, moving slowly enough to clump gravitationally, and light enough to have escaped detection, while being present in sufficient abundance to account for the observed dark matter density. The axions that emerge from Calabi-Yau compactification are not identical to the original Peccei-Quinn axion. They are a broader class, sometimes called string axions or moduli axions, with masses and couplings determined by the geometry of the manifold and the mechanism of moduli stabilization. Their mass is set by the depth of the non-perturbative potential that breaks the shift symmetry, which depends on the specific Calabi-Yau being used and the flux configuration threading its cycles. Different manifolds produce axions with different masses, different couplings, different cosmological abundances. Dark matter is here, in this room around you, passing through you, not as science fiction, but as the gravitational accounting of the universe's mass that does not resolve into any detected particle. Whatever it is present, and one of the serious proposals for what it might be, not the only one, not yet confirmed as the right one, is a particle whose mass and abundance were determined at the moment of the universe's formation by the shape of 6 compactified dimensions. The chain is long. Calabi-Yau geometry leads to moduli fields, leads to axionic partners, leads to dark matter candidates, leads to the invisible mass filling the universe. Each step in the chain is physically motivated. Each connection is grounded in the mathematics of the theory. And the chain has not been completed. There is no Calabi-Yau manifold that has been identified as the one producing axions with the right properties to account for the observed dark matter density. No compactification that has been confirmed as the geometric origin of what the universe cannot find. But the possibility sits there, geometric and patient, that what we cannot see in the sky was written into the shape of the hidden dimensions before the first second of the universe's existence. That dark matter is not an addition to the physics, not a new particle appended to the standard model from outside, but a residue, a shadow cast by geometry into the observable world, the 4-dimensional trace of a 6-dimensional shape that has been present at every point in space since the moment the extra dimensions compactified. This may be correct, it may not be. The geometry is permissive enough to accommodate the possibility without demanding it. And the distinction between accommodation and demand is, as this channel has had occasion to note before, a distinction that matters. What can be said is this: the shape of the hidden dimensions and the identity of dark matter are not, in string theory, independent questions. They are connected. How deeply, how directly, and whether the connection is ever confirmed by observation, that remains open, and honestly so. The honest answer may be no. Not definitely no, not no in a way that closes the question permanently or settles anything about whether the dimensions exist, but no in the sense that the tools currently available, and the tools foreseeable within any realistic extension of current technology, are separated from the scale at which the extra dimensions are predicted to operate by a gap that is not merely large, but large in a way that resists easy description. That gap is worth sitting with before the detection methods are described, because it sets the context for everything that follows. String theory, in its standard Calabi-Yau compactification form, places the extra dimensions at or near the Planck length, approximately 10 to the power of minus 35 meters, the scale at which quantum gravitational effects are expected to become significant. To resolve a structure at that scale directly would require a probe with a wavelength comparable to the Planck length, which by the de Broglie relation requires a momentum, and therefore an energy, of approximately 10 to the power of 19 giga-electron volts, the Planck energy. The Large Hadron Collider, the largest and most energetic particle accelerator humanity has built, operates at collision energies of roughly 10 to the 4th giga electron volts. The gap between the LHC and the Planck scale is 15 orders of magnitude, 10 to the 15th, a quadrillion. The LHC sits beneath the French-Swiss border, 17 miles of superconducting tunnel, cooled to temperatures colder than outer space, designed specifically to resolve structure at the smallest scales current technology can reach. It is the most powerful microscope our civilization has produced, and it falls short of the Planck scale by a factor that, if you tried to cover it with incremental improvements to accelerator technology, would take longer than the current age of the universe to bridge. This is not a reason to stop looking. It is a reason to look carefully at what might be detectable short of the Planck scale, and to be precise about what each potential signal would and would not confirm. The first and most direct prediction is Kaluza-Klein excitations. When a dimension is compactified, curled into a circle of radius r, particles that have momentum in that direction are quantized. The momentum can only take values that are integer multiples of the inverse radius. In 4-dimensional terms, these quantisaid momenta appear as masses, a tower of increasingly heavy particles, each one a copy of a known standard model particle, but carrying an additional mass set by the compactification scale. The electron has Kaluza-Klein partners. The photon has Kaluza-Klein partners. Every particle in the standard model has an infinite tower of heavier copies, each separated from the next by a mass gap determined by the size of the extra dimension. For dimensions compactified at the Planck scale, the standard string theory expectation, the lightest Kaluza-Klein excitation would have a mass near the Planck energy, inaccessible to the LHC, inaccessible to any conceivable near-future accelerator. The tower exists, in the theory, but its lowest rung is 15 orders of magnitude above the LHC's reach, not detected. The absence of Kaluza-Klein excitations at the LHC is consistent with extra dimensions compactified at the Planck scale. It does not constrain them, it does not confirm them. It is simply what you would expect to see, which is nothing, if the dimensions are where standard string theory places them. The ADD model changes this. In 1998, Nima Arkani-Hamed, Savas Dimopoulos and Giad Valley proposed a different compactification scenario, one in which the extra dimensions are not at the Planck scale, but are instead much larger. Much larger in a specific sense. The standard model fields are confined to a 4-dimensional brane, a membrane embedded in the higher dimensional space, and only gravity propagates through the full bulk of the extra dimensions. In this scenario, gravity appears weak at ordinary scales, not because it is intrinsically weak, but because it is diluted, spread across the volume of the large extra dimensions, leaving only a fraction of its full strength accessible to 4-dimensional observers. If the ADD model is correct, the extra dimensions could be as large as a fraction of a millimeter, a scale that is, in principle, accessible to precision tests of gravity. Newton's inverse square law has been tested at short distances using torsion balance experiments, extraordinarily sensitive instruments that measure the gravitational force between small masses at separations down to fractions of a millimeter. If extra dimensions exist at that scale, the inverse square law would show deviations. Gravity would fall off faster than expected at separations comparable to the extra dimension size as the gravitational field begins to spread into the additional volume. These experiments have been conducted. The Urtwash group at the University of Washington has tested the inverse square law down to separations of roughly 50 micrometers, about the width of a human hair. No deviations from Newton's law have been found at that scale. The ADD model, with extra dimensions larger than approximately 50 micrometers, is constrained by these results, not ruled out entirely for all configurations, but substantially tightened. The large extra dimensions, if they exist in the ADD sense, are smaller than the current experimental limit. The Kaluza-Klein excitations predicted by the ADD model would be lighter than the Planck scale versions, light enough in some configurations to be produced at the LHC. Searches for missing energy signals, events where a Kaluza-Klein graviton is produced and escapes into the extra dimensions, taking energy with it, have been conducted at the LHC. No significant excess has been observed. The constraints on large extra dimensions from LHC data have pushed the ADD model's parameter space into corners that are increasingly narrow. The Randall-Sundrum scenario offers a different geometry. In 1999, Lisa Randall and Raman Sundrum proposed a model in which our universe is a four-dimensional brain embedded in a five-dimensional anti-de Sitter space, a space-time with a specific negative curvature in the extra dimension. The curvature is arranged so that gravity is localized near one brain, falling off exponentially as you move through the fifth dimension. The extra dimension can be infinite in extent in this model without producing observable deviations from four-dimensional gravity. The warping of the geometry confines the gravitational field near the brain without requiring the dimension to be small. The Randall-Sundrum model predicts its own Kaluza-Klein gravitons, particles that are, in some configurations, in the TeV mass range and potentially accessible to the LHC. These have been searched for, narrow resonances in the diphoton and dilepton channels, which would be the signature of a Kaluza-Klein graviton decaying to standard model particles. Not detected to the sensitivity of current searches. The parameter space of the simplest Randall-Sundrum model is constrained, though not closed. What does the absence of detection mean? Not detected is not the same as not present. This distinction is precise and important, and it's easy to blur in a way that misleads. The LHC has not found Kaluza-Klein excitations. The torsion balance experiments have not found deviations from Newton's law below 50 micrometers. These are genuine constraints on specific models. They rule out specific parameter ranges of the ADD and Randall-Sundrum scenarios. They do not constrain Planck scale compactification, which is the standard string theory prediction, because Planck scale compactification was never expected to produce signals at LHC energies. The absence of large extra dimensions at accessible scales is a result. It is not a result about the existence of small extra dimensions at the Planck scale. String theory's standard prediction, 6 dimensions at 10 to the power of minus 35 meters, has not been tested because testing it is not currently possible and may not be possible for the foreseeable future, and may not be possible in principle with any technology derivable from known physics. Whether a dimension that cannot be detected is a dimension in any scientifically meaningful sense is a question that sits at the edge of physics and philosophy, and it does not have a clean answer. The positivist response, that an undetectable entity has no scientific standing, has a long history and a certain rigour. The structural response, that an entity required by a mathematically consistent framework has at least theoretical standing regardless of direct detectability, has a different kind of weight. Both positions are defensible. Neither is comfortable. The extra dimensions may be there. The geometry may be exactly as string theory describes, and we may never, in any practical sense, be able to check. This is not a conclusion anyone in the field is pleased about, but it is, at this particular moment in the development of the theory, where things stand. What comes next is not a detection method. It is a different kind of tool entirely, one that approaches the landscape not through experiment but through the mathematical structure itself. Using instruments built not of superconducting magnets and particle beams, but of data and learning. The Kreuzerskaka database contains 473,800,776 entries. Each entry is a reflexive polytope, a geometric object in 4 dimensions whose combinatorial structure encodes the data needed to construct a Calabi-Yau threefold. Each polytope can be triangulated in multiple ways, and each distinct triangulation corresponds to a distinct Calabi-Yau manifold with its own Hodge numbers, its own Euler characteristic, its own topological fingerprint. the number of triangulations grows exponentially with the number of vertices in the polytope. For polytopes with many vertices, the number of distinct triangulations, and therefore the number of distinct Calabi-Yau manifolds derivable from a single polytope, runs into the billions. The Kreuzer-Skarke database is the most complete catalogue of Calabi-Yau threefold constructions available. It was compiled by Maximilian Kreuzer and Harold Skarke in 2002 using an exhaustive computer search through all reflexive polytopes in 4 dimensions. The search was finite. There are exactly 473,800,776 such polytopes, a number Batirev proved to be complete for this class. The database is, in that sense, closed. Everything that can be constructed by this method is in it, and it is far too large for any human, or any group of humans, to examine directly. This is the problem the machines are being asked to solve, not in the vague sense of applying artificial intelligence to a difficult task, but in the precise sense that the landscape of Calabi-Yau manifolds is a combinatorial space of a size that places systematic human exploration outside the range of possibility. If a team of physicists spent their entire careers examining one manifold per day, computing its Hodge numbers, checking its particle spectrum, determining whether it produces anything resembling the standard model, they would cover, across a lifetime of work, a number of manifolds that rounds to 0 when expressed as a fraction of the full landscape. The landscape is not large in the way that a difficult computational problem is large. It is large in the way that a library is large when the library is bigger than the physical universe, when the search itself, conducted by any human instrument, cannot be completed in any time available to human civilization. Machine learning is not, in this context, a convenience or an acceleration. It is the only tool scale to the problem. The specific approach that has attracted the most recent attention involves transformer architectures, the same class of neural network that underlies large language models, adapted here not for language, but for the combinatorial geometry of polytope triangulations. The problem the transformers are trained on is the fine regular star triangulation problem, the task of generating all valid triangulations of a given reflexive polytope, where valid means satisfying a specific set of geometric conditions that ensure the resulting Calabi-Yau manifold is well behaved. For polytopes with small numbers of vertices, this is tractable by conventional methods. For polytopes with larger vertex counts, the number of valid triangulations grows exponentially, and conventional enumeration becomes computationally prohibitive. The CY transformer, described in a paper presented at the NeurEPS Machine Learning for Physical Sciences workshop in 2025, is trained to generate fine regular star triangulations directly, to sample from the space of valid triangulations of a given polytope, without enumerating all of them. It works by learning the statistical structure of the triangulation space from examples, developing an internal representation of which configurations are geometrically valid, and using that representation to produce new valid triangulations that it has not explicitly seen before. The results, benchmarked against conventional triangulation methods, show that the transformer recovers a substantially higher fraction of distinct valid triangulations per sample than conventional fast samplers, and does so more efficiently as the vertex count grows, precisely the regime where conventional methods struggle most. The machine is not better at small problems, it is better at large ones, which is, given what the problem is, exactly the right direction for improvement. What the machines are searching for ultimately, though this is a long chain from a neural network trained on polytope data, is the geometry of our universe. If string theory is correct, one point in the Calabi-Yau landscape corresponds to the specific compactification that produced the physics we observe. One manifold or one class of manifolds has Hodge numbers and an Euler characteristic that reproduce the standard model's particle content. The 3 generations of matter, the specific gauge group structure of the forces. That manifold is somewhere in the Kreuzer-Skarke database, or in an extension of it. Finding it requires navigating a space it is hard to find a word that fits without reaching for something excessive, a space that is genuinely too large to search by any method that examines each candidate individually. The machine learning approach does not examine candidates individually. It learns the structure of the space and samples from regions that are statistically more likely to contain physically realistic configurations. It is a search conducted not by walking through the library, but by learning the library's architecture and inferring where the relevant shelves are likely to be. Whether this constitutes understanding is a question the chapter cannot answer, and probably the field cannot either. The transformer learns to generate valid triangulations with high efficiency. It does not know what a Calabi-Yau manifold is in any sense that the word "no" usually implies. It has learned statistical patterns in data that happen to correspond to geometric validity conditions. The patterns are real. The geometry they encode is real. The relationship between the pattern and the geometry, whether learning the first is in any sense equivalent to understanding the second, sits in a conceptual space that physics and mathematics have not yet mapped. This is new, not as a rhetorical gesture, but as a factual description of where the field is. The application of transformer architectures to the fine triangulation problem, the systematic machine learning approach to Hodge number prediction, the use of neural networks to identify physically realistic corners of the landscape. These are developments of the last few years. The tools are the first of their kind that are actually scaled to the size of the problem they are addressing. What they will find, whether the landscape contains a configuration that cleanly reproduces the standard model, whether machine learning can identify it, whether the identification would constitute evidence that string theory is correct, none of this is known. The tools are new, the results are preliminary. The question is old and has not yet been answered. But for the first time, the search is being conducted with instruments that are at least the right size for the landscape they are searching. Whether that is enough depends on what the landscape actually contains, and that is a question only the landscape can answer. The geometry is there in the mathematics waiting. Whether the machines will find it, whether there is anything in that space that matches what we observe, is genuinely open and genuinely worth asking. The room you are in right now has a floor. You know this without checking, the way you know the ceiling is above you, the way you know that the walls are at a particular distance, the way the body keeps its own quiet map of the space it occupies and updates it without being asked. 3 dimensions, the floor below, the ceiling above, the walls at their distances, the geometry of a room, the geometry that has been the background of every human experience that has ever occurred. The stage, as the first chapter called it, on which everything takes place. Nothing about that room has changed over the last 16 chapters. The floor is still there. The air is still whatever temperature it is tonight. If you have a hand resting on something, a surface, a pillow, the edge of a blanket, the resistance is still there, the same pushback that opened this whole thing, the particular pressure of a boundary between your skin and something that is not you. And yet, at every point in that room, not metaphorically, not approximately, but literally at every geometric point, at every location in the space between you and the nearest wall, string theory predicts that 6 spatial dimensions are folded into a structure so narrow that its circumference is near the Planck length. A structure that has been there since the moment the universe cooled enough for the extra dimensions to compactify. A structure that has been present at every point in the cosmos, through every era of the universe's history, through the formation of the first stars and the first galaxies and the slow cooling of everything into the arrangement that eventually produced this room and the person in it. The Calabi-Yau manifold, that compact, reachy flat Kähler space with SU3 holonomy, carrying in its Hodge numbers the count of matter generations, encoding in its topology the structure of the forces, is not somewhere else. It is not in some distant region of the universe where the physics is different. If string theory is correct, it is here, in the air between your hand and the ceiling, in the space the room contains, at every point present geometrically exact, holding in its shape the laws that govern what matter is and how forces act and why the universe takes the specific form it takes. This is the claim. It has been examined from several directions across 16 chapters. It has not been confirmed. It may not be confirmable, at least not with any instrument that exists or is foreseeable. But it has not been refuted either, and the mathematics that supports it is precise and internally consistent and has produced, in the process of being developed, genuine advances in pure mathematics that exist independently of whether the physics is correct. What changes if you take the possibility seriously? Well, not the room. The room is the same. The floor holds you the same way. The air has the same temperature. Nothing about the experience of being in a three-dimensional space is altered by the possibility that 6 additional dimensions are folded into every point of that space, because the folding is at a scale so far below the resolution of any sensory apparatus, any nervous system, any instrument, that the experience of the space is completely unaffected. What changes is something more like the background, the thing behind the experience, the sense, or not quite a sense, more a thought that sits quietly, that the apparent simplicity of the space, the three-directional geometry that the body reads so fluently and so automatically is not the whole of it, that the room is more than the room reports, not in a mystical sense, in a geometric one, in the specific sense that a physicist means when they say that a space has structure below the resolution of available probes. The hand pressed flat against a surface of the same hand, the same surface, the same resistance that opened this, feels 3 dimensions. The pushback is real. The geometry it reports is real. And it may be the surface of a space that has 9 spatial dimensions, 6 of them wound into a shape that the hand cannot feel and no instrument can resolve, and the mathematics describes with a precision that the hand's pressure cannot approach. Kaluza wrote a letter. Klein made the dimension invisible. Calabi proposed a shape that shouldn't exist. Yau proved it did, on a Christmas day in 1976, in a quiet room somewhere, with no ceremony. 4 physicists in 1985 connected the shape to the theory. Hundreds of others extended the connection, found the landscape, discovered the mirror world, built the databases. Machines are now searching the databases for the one configuration or the class of configurations that matches what we observe. All of this tracing back to the question of why the hand feels 3 dimensions and not 9. All of this from the same basic unease that Helmholtz articulated in the 1860s, that our geometric intuition might be a property of our nervous systems rather than a fact about space. The shape beneath everything is, if the theory is right, exact. Not approximate, not nearly right. Exact. A specific class of geometric objects, satisfying specific mathematical conditions, present at every point in space, encoding in their topology the physical laws that govern everything that happens in the space they inhabit. The laws of physics may not be laws in the sense of rules imposed from outside. They may be geometry. They may be the 4-dimensional shadow of a 6-dimensional shape that has been present since the first fraction of a second of the universe's existence, patient and precise and entirely silent. Silent is, actually, that is not quite the right word. The shape is not Abden, it is speaking constantly in every particle interaction, every force, every decay and collision and quantum transition. What it is inaudible. Inaudible to us with the instruments we have at the energies we can reach. The speech is there. We have not yet built the ear, and perhaps we never will. Perhaps the geometry will remain, as Klein first suggested, permanently beyond the reach of any probe our civilization could construct. Perhaps the machines searching the landscape will find a configuration that matches the standard model exactly, and the match will be the closest thing to confirmation available. Not a direct detection, but a coherence, a resonance between the mathematical structure and the observed world. Perhaps. The word carries its full weight here without apology. The room is the room, the floor is the floor. The hand rests against whatever it rests against, and the resistance is real, and the geometry the resistance reports is real, and beneath that geometry, something, folded, present, exact. You are the reason this place exists. Every episode here is built without outside funding, without sponsorships, without anything except the people who choose to support it. If you want to help the Sleepy Physicist continue to grow, the Patreon link is in the description. It means more than these episodes can say.